Hello everyone. So this class we are going to discuss about the concepts, that is the theoretical concepts of heat sink performance. Last video I have uploaded regarding the modeling of heat sink using ansys ice pack. So that was uploaded in 3 parts. So this theory will support the practical part. We have seen like step by step how it was modeled and how to evaluate its performance. That is the thermal heat transfer, the efficiency of the heat sink that we have seen. So this theory will help you like what are all the physical significance of the parameters that really affects the heat sink performance. So in this class we are going to see about air cooling and heat sinks. So when I say types of cooling, that is normally we take a flat plate. There can be 2 types of cooling. One is the active cooling and other one is a passive cooling. When I say active cooling, I am going to use an external medium. Okay, it can be a fan or some other equipment. So that is not called as active cooling. The other name of active cooling is forced convection. When I say passive cooling, it is referred to as free or natural convection. That is normally air that is flowing past a plate will help to remove away the heat, the normal convection. Okay. So when we look at the practical aspects, that is how complicated the system is, whether maintenance of the system is easy or difficult, based on that we can choose whether we need an active cooling or a passive cooling. So when it comes to cost wise, we normally stick to passive cooling only, but in case of electronic equipments, we see that the heat transfer, that is the heat should be dissipated to a higher extent. So in that case, this forced convection is being preferred. So we are choosing the forced convection, but still the maintenance cost and other things should be low. So what are the methods that can be employed? Okay, so that we will be discussing in this session. So here you can see one electronic gadget I have taken. So there are various components inside. Now you consider a PCB, a printed circuit board. So there are various components and the spacing between the components also varies. So as the spacing varies, the flow between those spaces is also different. So the forced convection should be chosen in such a way that it accounts the heat transfer against that flow path. Okay, wherever the heat is there, so everything has to be dissipated out to a maximum extent. So when we consider a simple PCB, there is always 2 components. In fact, there are 3 components. One is heat transfer from the base of the component to the PCB, that is by conduction, from the PCB to the air, so that is convection, and again from the component to the air by radiation. So these 3 processes are occurring. So this is the types of cooling. Why forced convection? Why natural convection? If it is forced convection, what are all the parameters that we are going to consider? Here I have taken a simple straight fin heat sink. So this is going to represent natural convection. I haven't placed any fan or a circulating pump or nothing by the side. So this is called as a heat sink, and the fins that are used are straight fin type only. You know there are different configurations like triangular fin, cylindrical fin, tapering type of fin. So this is straight fin. You can see the cross section at above and below all are the same. And 3 major parameters are length of the heat sink, height of the heat sink, width of the heat sink. Okay, we usually keep the length, width and height of the heat sink constant only. We are going to vary something called as this distance S. So that distance is called as fin spacing. The spacing is only going to vary. Of course, the thickness of the fin can also be changed. So when the spacing is going to vary, the number of fins that are used is going to be different. Now, I have told you the height, length and width of the heat sink. Fin spacing means what? Fin thickness means what I told you. Now, there are so many research works experimented on this area, that is dissipating, removing the heat from electronic gadgets, that is from say PCB itself. So here from one such study I have taken a graph. So in this graph you see the natural convection heat loss is studied from finned heat sink, that is fins are there, okay, with width of 40 mm. So they have taken the width as constant. Look at the right side legend, the length is varied from 30 to 60. So length of the heat sink is varied from 30 to 60. Now the fin spacing is varied from 2 to 12. let me take this one first graph. This first graph represents length of the heat sink at 30 mm. So at 30 mm, what I notice is at 4 mm fin spacing, I have a BTU of 4. At 6 mm spacing, I have a BTU of 4.1. At 8 mm spacing, I have a BTU of 3.5. So as the spacing keeps on varying, the heat loss is also different. So that is what is understood here. So when I consider the next length of the heat sink, that is 40 mm, so this is my second curve. Here also you can see that there are different values of heat loss. So as the length of the heat sink varies, there are different values of heat loss. That is first thing. The second thing is, in this first length itself, if I consider the fin spacing, that is 4 mm and 6 mm, for both the values of fin spacing, I notice that the heat loss is more or less equal. Here it is 4.1 and here it is 4, that's all. There is no much variation in the heat loss, right? So instead of going for a 4 mm spacing, I can very well adopt to 6 mm spacing. I can tell you what is the advantage of 6 mm spacing. If I am using a 6 mm spacing, the number of fins used will be less and it is not so much congested. So you don't have to worry much about the flow path. We saw that the flow path against the different components varies depending on the spacing, right? So it is always preferable to have a 6 mm, that is more spacing. So I can easily adopt to this. So in this study you understand that the length of the sink is going to affect the heat loss. Likewise, you can decide at the optimum level of the fin spacing, right? Next is the forced convection. So see, though simplicity and easy maintenance are inbuilt components of natural convection, we still go for forced convection. The reason is, though the gadgets used are very small, the heat dissipation may affect the performance of the gadget, so that has to be fully removed. So when I say effective removal of heat loss, I obviously have to stick to forced convection only. Okay. So different types of heat sinks are often mounted on the components to make this possible. Now coming to we understood what is heat sink. What is its purpose? What type of convection we are going to adopt? What is fin spacing? This is what we understood so far. Now, when I say the heat sink performance, whether it is performing well, how will I say it is performing well? Only when I look at the heat dissipation. More the BTU, more the heat loss, more the performance. So to increase the heat thermal resistance, to increase the performance, I will be targeting one parameter called as thermal resistance. So we know that more the resistance, the heat dissipation will be less. Less the resistance, it will be more. So this thermal resistance is what we are always concentrating into. But the other thing that comes into action is called as pressure drop. So when I keep more number of fins, obviously the heat sink will be performing very good. But at the same case, there is a higher pressure drop. So I am achieving my target at the cost of something. So that is called as pressure drop. Now look at this curve. The thermal resistance keeps on decreasing, which means the heat transfer is more. But as it keeps on decreasing, you can see the pressure drop is also increasing, right? So we normally concentrate on this, but we forget to pay attention to this. That should not happen. We'll have to consider both and then design the system. Now looking at the thermal resistance, when I say total thermal resistance, it is comprising of two different parameters. The first one is the average heat sink resistance and the second is the heat sink spreading resistance. So what is this average resistance and what is the spreading? So average heat sink resistance is from the fin to the surface, to the air. Whereas when it is spreading resistance, it is from the base of the fin to the other parts. So when I say from the base means it's obviously convection only, heat contributed due to convection. Whereas this average heat sink resistance means it comes from the heat that is contributed by convection from the body of the fin to the surface, right? So these two resistances clubbed together is called as total resistance, right? And you look at this equation, you will understand that the total resistance is a function of the heat transfer, and this is again dependent on few other quantities. So this is the overall efficiency, heat transfer coefficient and the total fin surface. right? So whenever I have to decide what value, this value I would have given in the ISPAC tutorial, we'll be fixing this value, right? So when we fix this value randomly, I cannot give 3.5, 4.5. This is dependent on these, that is overall efficiency of the fin, surface area of the fin, and heat transfer coefficient. Okay, now the last topic for this lecture, factors affecting heat sink thermal performance. There are three factors which affects. The first one is flow bypass and flow leakage. The second one is fin configuration, and the third one is mass flow rate. Now I'll explain the difference between this flow bypass and flow leakage. Now you can see a device, a channel you can see. So inside that there is a heat sink. There will be a flow rate of air flow rate which is entering this heat sink and exiting the heat sink. Likewise, there is another volume flow rate of air which is entering this channel and exiting this channel, right? So now we have two inlets. One is inlet at the sink and other one is inlet at the channel. The difference between the inlet at the sink and the inlet at the channel, that difference you call it as flow bypass. Okay? Now you see, as the flow is occurring, there are chances for air to go through this different sinks, the fins, and then come out. There is also chance for the air to just bypass this and go like this. Air is really very clever. It has the tendency to just skip the path which is having more resistance, right? So this is having more resistance, so it will obviously move like this. Okay, so this is again a loss. This is called as flow bypass. The second one is flow leakage. So flow leakage is, here I have taken only the heat sink, the inlet flow is given and the outlet flow is given. The difference between the outlet flow rate of the heat sink and the inlet flow rate of the heat sink is called as flow leakage. Right? So these two parameters should be considered when you are talking about the heat sink thermal performance. And then the second one I told, the types of fin. When I say types of fin, it is the design of the fin. We already know what's the difference between fin spacing and number of fins. So here you can see the fin configuration. The first one represents extrusion type of fin. The second one is plain fins. You can see the C type of structure, and the next is the cell fin. So these are the three types. So out of numerous studies conducted on the comparison of performance of these design configurations, it is understood that the cell fins has got more surface area. So higher the heat transfer coefficient, higher the heat transfer. So this is preferred. The main difference between these three types is the length of the heat sink, width of the heat sink, then the height of the heat sink, all remains the same. Material also remains the same. The only difference is with respect to the cell spacing and the number of fins. So here you will see that there is more number of cells, more heat transfer coefficient, so more heat transfer, better I can say heat dissipation. But along with that, we are doing it at the cost of pressure drop. So the pressure drop in the cell fins will be higher. Yes, and the third one is a mass flow rate. So we very well know that heat transfer, that is thermal resistance, is dependent on mass flow rate. So when I say mass flow rate, it is rho AB, right? Or when I say mass velocity, it is rho into V. Now whether to consider mass flow rate or mass velocity, that will tell you how accurately you have designed your problem. When I say mass velocity, it is rho into V. So you take that value as G, parameter equating it, that is rho into V is equated to G. Now the variation of this mass velocity will be 0.5 times for that of a laminar flow, whereas it will be to the power of 0.8 times for a turbulent flow. So to this much extent it will affect. So when you know that the mass velocity is increased, obviously your thermal resistance will also be inversely, okay, it will be affected. So most of the cases, in most of the theoretical cases, what we do is we will only consider the mass flow rate, we will forget to account for the mass velocity. So for the calculations to be very apt, we will have to consider the mass velocity, see how it affects the thermal resistance and then the heat transfer coefficient, and then design the problem. So these are small errors like which we don't, otherwise we consciously neglect or we think that we are making the problem more simplified and we are doing it. Okay, so this flow bypass and leakage should be considered. Proper fin configuration, we'll definitely go for choosing the proper fin material. Okay, thickness we will choose, and spacing we will choose, number of fins we will choose. But fin configurations, again the type of the fin. So how much we saw, right? Only in the cell fin we were able to get a very good thermal resistance. So low thermal resistance. So this is that importance. And the last is the mass flow rate, which I've explained. So I've given a reference. You can just go through this book series. It's very important. So learning the theory part as well as going by the design, that is experimental part, will give you a better understanding, I believe. And thanks for watching and for your support. Thank you.